Okay, students, today we won't have class because a number of you have other commitments, so I'll still do a little lecture and I'll put a little link to the video here. Today we're going to discuss a very important result involving group theory. We're going to look, kind of remember back to when we work with the fruits here. We have two separate groups of order 4. We have what's called the dihedral, which involves actions on a piece of paper, flipping. So cantaloupe means do nothing. Apple means to flip. Pear means to flub, which means I'm kind of turning the page this way. And grapes means to flip and then flub. So I got do nothing, flip, flub, and flip flop. Now the cyclic group of order 4, that's a separate group of order 4. That involves a piece of paper like this, just the front side. Cantaloupe means do nothing. Banana means to turn once. Orange means to turn twice, once, twice. And pineapple means to turn 3 times, once, twice, thrice. Now we look at what we call the dihedral group of degree 3. We call it degree 3 because we're acting on a polygon with 3 sides, with 3 vertices. And there are a variety of different things I can do. Cantaloupe means to do nothing. Banana means to turn once. Orange means to turn twice, once, twice. And apple means to flip. Grapes means to flip and then turn once. And finally, pineapple means to flip and then turn once and then twice. And so now we have 6 elements in this group. Do nothing, turn once, turn twice, flip, flip turn, and flip turn. That's flip and then turn twice. So we have a group of order 6. Now we're going to look here, and we're going to look at and study what we call a subgroup. A subgroup is a subset of the group, which itself can form a group. So let's take a look at the Theorem, which means in German means a group with 4 elements. What are the different subgroups here? So you might study this a little bit. You can see that there are 3 proper non-trivial subgroups. So every group has at least one subgroup, the trivial subgroup, which is just identity element itself. So the subgroups are the identity element itself, which we could call the trivial subgroup. We have then 3 other proper subgroups. We have cantaloupe apple, cantaloupe pear, and then cantaloupe grapes. Cantaloupe grapes. Now we have the whole group itself, which is itself a subgroup, so that's the improper subgroup. So we're not going to consider the improper subgroups, that's the whole group itself. We're going to consider the proper subgroups, the proper non-trivial subgroups. There's 3 of them. Cantaloupe apple, cantaloupe pear, cantaloupe grapes. What about the cyclic group of order 4? The cyclic group of order 4, there turns out to be only one proper non-trivial subgroup, and that's just simply cantaloupe and orange. Cantaloupe and orange. So what that means is that I can construct a multiplication table involving the elements of the subset. So here, only cantaloupe and orange can form a subgroup. So as you recall, a group is a non-empty set of elements that satisfies 4 conditions. Well, non-empty set of elements and a operation called product, such that there's closure, such that there is associative property, such that there is an identity, and such that every element has an inverse. Now let's look at our dihedral group of degree 3, which we actually saw is isomorphic, has the same structure as the symmetric group of degree 3. The symmetric group being the group of all mappings of 3 elements onto itself. There's 6 elements. Those 2 groups are isomorphic. Now here, let's try to figure out what the subgroups are. We have, of course, the trivial subgroup, which is the cantaloupe itself. But we have cantaloupe, banana, and orange forms a subgroup. And then we also have cantaloupe and apple, cantaloupe and grapes, and then cantaloupe and pineapple. So here, and then of course we have the whole group itself as a subgroup, but that's called an improper subgroup. So the number of proper non-trivial subgroups is 1, 2, 3, 4. There's 4 proper non-trivial subgroups. Now look at these subgroups here. There's a subgroup of order 3, 3 subgroups of order 2. This is a group of order 6. What sort of pattern do you see? What sort of thing do you see that you feel like relates the order of the group and the order of the subgroup? So we're going to pause for a moment over here. So think about it. So you can stop the video right now. Think for about 10, 15 seconds. What do you think relates the order of the subgroups and the order of the group? We're going to wait. Yes, you are right. It turns out that the order of the subgroups divides the order of a group. So for instance, can a group of order 6 have a subgroup of order 4? The answer is no, because 4 does not divide 6. So it turns out in order for a group to have a subgroup, the order of the subgroup must divide the order of the group. Now, if there's a number that divides the order of the group, that doesn't necessarily mean it has a subgroup of that order. So you might have a group of order 100, and you might say, hey, the group of order 125 divides 100. That doesn't necessarily mean that group of 100 has a subgroup of order 25 from Lagrange's theorem. Lagrange's theorem states that the order of a group, Lagrange's theorem states that if H is a subgroup of a finite group G, then the order of H divides the order of G. This is a very, very important theorem in group theory, and this is called Lagrange's theorem. So in our next class, we will prove Lagrange's theorem. So again, to summarize, given a group gives a group order 6, it turns out that if this group has a subgroup, the order of the subgroup must divide the order of the group. And that is called Lagrange's theorem. So that's a very important theorem. The converse of Lagrange's theorem is not necessarily true, because you might have a number that divides the order of the group. That doesn't necessarily mean that the group has a subgroup of that order. So that's a much, much deeper, more complex problem is determining when a group has particular subgroups. But we certainly know from Lagrange's theorem that if a group has a subgroup, if H is a subgroup of a finite group G, then the order of H divides the order of G. So that concludes our lesson. I hope that you all have a wonderful day. If necessary, rewatch this video. You don't necessarily, just to let you know, when you look at these Caley tables, these are like kind of the multiplication tables for the group, you don't necessarily have to know the underlying reason behind these charts, the flips and the turns and all that other stuff. We can look from this table, we can verify that the rules for a group apply. So we take the little actions on the triangle, on the rectangle, the flips and the flubs and all that other stuff. We can throw that out and just look at these multiplication tables. So best wishes to y'all. I thank my assistant Samantha Chappell for filming this little video lecture, and have a wonderful day. So long.